one remote. For the attendance online, if you don't want to appear in the recording, please turn off your camera now. And the first speaker of today is Jin Leung. I hope I pronounced it correctly. Jin did his PhD at UC San Diego, working on AGN feedback at Redshift with most depth survey. He is now a postdoc at JWST, working on galaxies and supermassive black holes in the early universe using Sears and NGD surveys. The field is yours.
Well, thank you, Andreas, for the introduction. So, I'm Jin Leung. I'm a postdoc at UT Austin. In this talk, I'll tell you about results on the high redshift universe using JWST observations. In particular, I'll focus on the UV luminosity function and little red dots. So this work is done in collaboration with Steve Finkelstein, Michaela Beckley, and also the Sears and NGD collaborations. So one of the primary science drivers of JWST is to observe the galaxy population in the first billion years. And in fact, within the first year of JWST's observations, it has already led to two surprising results at these early epochs. So the first surprising result is that the abundance of bright galaxies at redshift greater than 9 exceeds both theoretical predictions and empirical expectations. So from this, the question will be, what does it tell us about the physical mechanisms of galaxy formation at these epochs? And the second surprising discovery is that we find a large population of red compact sources at redshift greater than 4. So could these sources be the sites of early supermassive black hole growth, or are they very massive galaxies that could potentially break our understanding of the universe? So in my talk, we'll try to tackle both of these problems. The first part of my talk will focus on the UV luminosity function at redshift greater than 9. So the luminosity function of galaxies is an important way to measure the galaxy population, and it also tells us about different physical mechanisms that govern how galaxy looks like. And different parts of the luminosity function tell us about different mechanisms. So on the left, we show an example UV luminosity function. And you can see the right end is on the left side of the plot. And this end of the luminosity function is governed by AGN feedback or star formation laws. And on the right side, you have the same end of the luminosity function where number densities are higher, and this side is governed by the physics of stellar feedback. So to have a complete understanding of the galaxy, the mechanisms of galaxy formation, we need to map the UV luminosity function throughout the nanotube range. So the commissioning of JWST has transformed our capability in measuring high redshift galaxies, and it has allowed us to measure the luminosity function at redshift greater than 9 in unprecedented ways. So on the right, I show the exposure maps of all the JWST Cycle 1 public imaging programs, and we can see a wide range of programs in terms of their areas and depths. You see very wide programs such as Cosmos Web, and you can also see intermediate programs like Sears with smaller area but deeper exposures. And finally, you can also see very deep programs such as NGD that focuses on a small area. So in the following, I'll focus on my work on the NGD survey. So an overview on NGD. NGD is a 100-hour cycle 1 program that is a nearest and near-time parallel program targeting the HUDF and HUDF parallel QT. So as the name NGD suggests, it's meant to be a deep field. And in fact, it is the first public deep field conducted by JWST. And it's also currently the deepest public geo-imaging data sets by JWST. So here you can see a beautiful color image of the mosaic of the full NGD field. So currently, the first epoch of NGD has been completed in February this year, and the second epoch is going to be taken in January or February next year. So The most relevant to my research is the NearCam data within NGD, which covers 1.1 to 4.5 microns over 6 filters in about 10 square arc minutes. And in NGD, I'm reading the data reduction of the NearCam imaging and also the production of the volumetric catalogs and data products. So using the ultra deep imaging in NGD, I've identified a sample of 38 galaxy candidates. And here's an example Redshift 12 galaxies in our sample. So using this galaxy sample, we measure the UV luminosity function at Redshift 9 and 11. On the left is the Redshift 9 luminosity function where the NGD points are shown in red. And on the right, we show the Redshift 11 UV luminosity function before NGD. The orange points are from Sears, which is a slightly larger but shallower survey. So with Sears, we're able to reach magnitudes of -19 or -18.5. And with the addition of the deep NGD imaging, we're able to reach fainter magnitudes of down to -17. So this helps us bridge the gap towards the faint end of the UV luminosity function. So in this plot, we show in the red shaded region a best fit double power law function to both luminosity functions. And in the gray shaded region, we show empirical extrapolations of the luminosity function from lower redshift. So these extrapolations are calibrated from redshift 0 to 9. So when we compare the red and gray shaded regions, in particular at redshift 11, we see that our observed luminosity function is at the high end of empirical extrapolations. So this suggests that the evolution of the luminosity function between redshift 9 to 11 is slow, which means that the number density of galaxies is not decreasing by as much as what we would expect from lower redshifts. So next, we compare our luminosity function with theoretical predictions. Here we plot the same red shaded region and we overplot it with different model predictions from theoretical models. So these models include hydrodynamic simulations, semi-analytic models, and empirical models. And in general, when we look at the faint end, we see that the observed luminosity is at the high end of theoretical predictions. It's higher than some models, but it can still be reproduced by some other models. However, when we move to the bright end and magnitudes brighter than -20, we see that the observed luminosity function is basically higher than almost all theoretical predictions. So this suggests a significant excess of bright galaxies at redshift 11 as we use JWST observations. So an interesting question coming from this will be how far does this excess extend? So with the current limits in the area of JWST observations, we can only probe down to magnitudes of -22, and to probe brighter magnitudes, we need larger areas. So this brings us to the Sheila survey. So Sheila is a combined ground and space-based photometric survey covering 0.3 to 4.5 microns. It has a very large area of 27 square degrees. And this area is 50 times larger than Cosmos Lab, which is the widest JWST survey to date. So in Sheila, I led the efforts of producing the model-based photometric catalog using a light profile fitting approach for over 4 million sources. So using the photometric catalog in Sheila and calculating photometric redshift, we searched for redshift greater than 10 galaxy candidates, and we found 10 of them. And these sources, some of the examples shown here, these sources are extremely bright. They have absolute magnitude of -25. And if confirmed, they will be the brightest objects known at this redshift. And we have obtained HSC follow-up observing time to better confirm the redshift of these objects. So on the right, we show a fiducial luminosity function, assuming 1 to 10 of these galaxy candidates being confirmed. And this shows that even if one of these objects are confirmed, it will suggest an excess and the UV luminosity function extending to very bright magnitude, unreachable by current JWST observations. So while these are a few objects, it will motivate larger scale searches for these extreme monsters at early times using future data sets such as Eclipse or Leung. So next, I will discuss several possible explanations of the bright end excess that we observe. So to produce the excess, we'll either have to make the objects brighter or we'll have to make them more massive. So these explanations will tackle the problem in one of those ways. So the first possible explanation is that there's significantly less dust attenuation at high redshift. So this is the assumption of the Ferraro 23 model. And basically in this scenario, at early times, dust in the galaxy is cleared by very efficient feedback when the specific sound emission rate is high at high redshift. And the second explanation could be a top-heavy IMF at early times, where the abundance of massive stars could lead to a boost in the light-to-mass ratio, and therefore make the galaxy in UV. And then the third explanation could be more efficient or enhanced star formation at early times, when the gas density is high in a more compact universe. This could lead to more efficient conversion between gas and stars at early times. And therefore, the galaxy is more massive and brighter. Also, there's the possibility of stochastic star formation. In this case, the burstiness in star formation will lead to a variability or scatter in the overall UV luminosity. But because there are more faint galaxies than bright galaxies, it's more likely that the faint galaxy will be upscattered to bright magnitude than if a bright galaxy is downscattered. So the point to note is that for all of these processes, if it is applied uniformly throughout the magnitude range, it is still going to lead to a uniform boost in the UV luminosity function. So in order to produce the excess of the bright end only, these processes will have to have some sort of luminosity dependence so that it reproduces the observed data. So right now, these four scenarios are very degenerate with the current data that we have. But in the future, very deep spectroscopy of high redshift galaxies will have to distinguish these mechanisms. So this concludes the first part of my talk. In the second part of my talk, I will talk about a curious population. Yeah.
So since you're finishing this piece, is it ruled out that it's a quasar?
So far, there are some spectroscopic follow-ups of some of the higher, brighter, higher shift candidates, but you see some of them have AGN contribution, but it looks like it's not the majority. Yeah. Any other questions? Yeah.
Do we know how dust forms in this convection? Do you expect the dust to have the same properties? Because you said that there is less extinction, but you assume that dust is the same.
Yeah, so from what we find in the UV continuum slope of high redshift galaxies, we do see that they generally have very little dust. So, yeah. So let me move on to the second part of my talk, which is about the curious population at redshift greater than 4, known as little red dots. So since the early days of JWST observations, a peculiar population of objects have been showing up everywhere in different fields and different programs and different data sets. But they all have something in common. So first, they have a very characteristic two-component SEP, and that's characterized by a blue red-frame UV slope and a very red red-frame optical continuum. And secondly, they are all very compact in terms of their morphology, and you can see they're literally a little red dots. And third, they are mostly found at redshift greater than 4. So what is the potential physical natures of these objects? So in the early days, when we try to just fit the near infrared spectrometry of these sources, we find that it could be consistent with galaxies with very high stellar masses of more than 10 to the 10 solar masses. And this could potentially challenge our understanding of galaxy formation or even the smaller view. More recently, in the 323 paper, they looked at the Grissom spectra of about 10 little red dots, and they find that most of them have broad boundary emission lines, and that would suggest that there's at least some AGN contribution in many of the little red dots. However, this is only from a small sample, and to make more definitive conclusions to the nature of these objects, we need to scale this up to a larger sample size. So an effective way to study a large number of little red dots simultaneously is using MIRI imaging observations. So here we show the best fit SCP models to the same little red dots using two models. On the left, we show that fitted by a star-forming galaxy, and on the right, we show that fitted by an AGN model. We find that while both of these models can fit the near-infrared satisfactorily, the two models really diverge in the mid-infrared wavelengths. So for the star-forming galaxy, about 10 micron, there's a turnover in the mid-infrared emission coming from the stellar continuum. And for the AGN model, the mid-infrared emission keeps getting brighter due to the hot dust being heated by the AGN. So MIRI observations at greater than 10 microns is crucial in distinguishing these two scenarios. So to tackle this problem, I'm currently using data from the primer survey to study the MIRI photometry of little red dots. The primer survey is ideal for this purpose because it contains 200 square arc minutes of MIRI observations in the F770 and F1800 filters. And here we show where the filters are. You can see there's a perfect coverage of the hot dust emission in the AGN model with the F1800 and F770 filters. And on the other hand, in primer, we have simultaneously near-term coverage over the near-infrared emission, which allows us to select little red dots by their near-infrared two-component SCP. So with the primer survey, we have a preliminary analysis in primer cosmos, and we selected 66 little red dots with MIRI coverage in this field. And I'll focus on this sample. So here we show the mid-infrared colors of these little red dots. We show a color diagram, including two MIRI filters and one near-term filter. The little red dots are shown in the red points, and we also overplot templates of AGN and star-forming galaxies in the same plots. So the AGN templates come from Redshift 5 and greater quasars, and these star-forming galaxy templates come from templates within the easy photometric probe that includes both dusty and normal star-forming galaxies. So we can see that the little red dots can be divided into two populations, with about 3/4 of them having mid-infrared colors consistent with those of star-forming galaxies, and about 1/4 of them with mid-infrared colors consistent with that of AGN. So to have a closer look into the mid-infrared emission of these little red dots, I perform SCD modeling to individual sources using SIGAL. And here we show two examples of them. On the left, we show a little red dots where the mid-infrared is consistent with an AGN, and on the right, we show one where it's consistent with a star-forming galaxy. So in the left hand, on the top panel, we show the best fit models without including MIRI. In the left panel, we show the total model, where the AGN model is shown in orange and the galaxy model is shown in blue. In the next two panels, we show the individual components of the AGN and galaxy fits, where the AGN is in orange, the stellar component is in blue, and the galaxy dust emission is shown in green. So we find that without including MIRI, those models can fit the near-term data pretty well. But once we include MIRI, which is shown in the bottom panel, we find that these two sources really diverge in terms of their mid-infrared emission. For the left one, the mid-infrared continuum keeps rising after 4 microns, and that can be well fitted by an AGN template. But for the source on the right, the mid-infrared emission shows a turnover, and that is consistent with the stellar continuum of those wavelengths. And we find that for this source, if we are going to fit an AGN component to it, the AGN emission would dominate the Western UV, but not in the infrared. So this shows two populations of little red dots with different behaviors in the mid-infrared emission. So what is the physical nature of little red dots, given what we already know about them, and also from our new analysis? First, we find that there's a smaller portion of little red dots, where the mid-infrared emission is consistent with that from an AGN. So for this population, their properties are very similar to extremely red quasars at cosmically. And extremely quasars are known to be a transitional phase between an extruded AGN and extruded AGN. Secondly, we find a larger portion of little red dots where the mid-infrared emission is consistent with that of the star forming galaxy. So if we combine that with the fact that in the June and now 23 study, that a large portion of them have brought primary emission line, this would suggest that there is still at least some AGN contribution in the Western optical. And from our SED modeling, we find that the AGN emission can still dominate the Western UV. So in this case, these objects could potentially represent dust efficient AGN, where the lack of dust leads to the lack of mid-infrared signatures. So in conclusion, little red dots could represent AGN populations with different dust compositions. So to make more definitive conclusions on the nature of these objects, we really require large-scale spectroscopic follow-up with a larger number of little red dots, or morphological analysis, but the images of different wavelengths will also help us distinguish that from a host galaxy or from an AGN. So this concludes the second part of my talk. And in the third part of my talk, I will very quickly talk about the vertically integrated program, also known as VIP, at UT Austin. So at UT Austin, I'm currently the postdoc lead of the Galaxy Acquisition VIP program. It is a course-based undergraduate research experience aimed at increasing the STEM major retention rates of underrepresented groups. Right now, we're having a group of about 15 students. So VIP is characterized by a few characteristics. So first, we emphasize multi-year participation in projects where students progress from a starter project to a capstone project. And we also use a multi-level mentoring structure, and the mentoring team includes postdocs, graduate students, and even the undergrad themselves can serve as some form of mentorship roles. So here I'll quickly show one example student started project. So in this project, a student using machine learning algorithm known as TSNE to classify images of high redshift galaxy candidates. So this algorithm takes the image and reduces the dimension into 2 dimensions and groups similar objects together. And this is helpful in separating real detection of high redshift galaxies from those of potential spurious detection artifacts. And you can see the artifacts are shown grouped near the edge, and the better sources are grouped in the center. So this will help us both save time in selecting high redshift galaxies, but also make the selection more reproducible. So if you want to know more about VIP or TSN, you can come chat with me. So we're at time, so I'll leave it at the summary slide, and I will take any questions.
Thanks for the come on, don't be shy. Please, feel free to shout.
Dots, red, 5 bands. You gotta take care of what red is really trying to see. I would have thought it would be excess dots. That's the reason. So what is the fundamental reason these things are red?
Yeah, so from the SE modeling, if it is red throughout, from the indirect throughout the mid-infrared. So that would come from the dust emission in the AGN itself. But if there's a turnover in the mid-infrared emission, then it's probably just a static improvement. Right, we have not done that before, yes, but yes, that's definitely something to try. But right now there's a lot of degeneracy being between whether if that's just a model or we can.
Final question?
Yeah, very nice talk. I was interested, you said that maybe followers select about 75% start forming 25% each year. How can we be sure that those color selection criteria for this kind of I'm just asking about that.
Yeah, so definitely that's a very good question. So those colors that we compare to, they come from known templates of galaxies or AGN. We try to get as realistic templates as possible. So AGN comes from Redshift 5 or the AGN. And we also try some known dusty southern galaxies or Redshift 6. So we find that generally for those young sources, they fall within where they should be. But yes, for little red dots, there's still a lot of unknowns. And that's why I think the SED modeling will be actually more informative than just the
Okay, excellent. Let's thank. We had still a lot of slots, so feel free to sign up to meet with him. And let's move on to the second speaker of the day. Second speaker is Sandra Raimundo. She did a PhD at the Institute of Astronomy of the University of Cambridge in the UK, followed by postdoctoral position at CISA in Trieste, Italy, and at the Innsbruck Institute in Denmark. She then became a Marie Curie Global Fellow and assistant professor at the University of California, Los Angeles, and at the Innsbruck Institute. She is now a tenured assistant professor at the University of Southampton in the UK, and she will give a talk about fueling supermassive black holes with gas interactions. Sandra, whenever you want.
Hi, everyone. Thank you. Let me just set up the presentation.
Sandra, can you make like full screen?
Yeah, can you see it now?
We see like a side panel.
Okay, let me see. Let me try again. Okay, can you see it full screen now?
Yes.
Yes, okay. Thank you. Thank you for the introduction. It's a pleasure to be here remotely, but it's very nice to have the opportunity to share some recent research results with you. So the topic of my talk will be how to fuel supermassive black holes. And just to give you an outline of what the structure of the talk will be like. So first I will introduce the main problem that we're trying to address with the work. And that is the problem of black hole fueling. How are black holes fueled and how do they grow? And then I will introduce galaxy interactions and how misaligned gas from these interactions can be a source of fuel for black holes. And then I will move on to the results of our work, where we find a link between misaligned gas and active black holes, so active galactic nuclei or AGN. And then I will move on to a discussion. So put the results into context. What does it mean for galaxy evolution and black hole activity? So the main problem that we are focusing on is black hole fueling. So we know that black holes grow, they're active for a fraction of their lifetimes, but they need gas to fuel that activity. And the problem then is how does the gas reach the black hole? It's coming from the host galaxy, but somehow it has to be transported all the way down to the center to then fuel the black hole. And the broader question even is, why are some black holes active? Why are some AGN and others are inactive? And we think that there are two ingredients that are needed for the process of black hole fueling. And that is first, the supply of gas available to the black hole. And the second is a mechanism or mechanisms that are able to transport the gas from the host galaxy down to the black hole. So this is the general problem that we're focusing on. And interacting galaxies, so galaxies that interact with each other and their environment, they can provide this supply of gas that black holes need. So when two galaxies interact, in some cases, there can be a transfer of gas from one galaxy to the other. And for the rest of the talk, I will refer to this as external accretion of gas or an external accretion event. So this is when gas from the external environment is accreted by the galaxy. And this can be via mergers, tidal interactions with neighbors, flyby. So there's several possible mechanisms that could cause one of these external accretion events. And when these events happen, so you have a galaxy that is secreting gas from its external environment. And in some cases, the gas will end up misaligned with the stellar body of the galaxy. So here in this Hubble image, you see, I don't know if you can see my cursor, but in the horizontal direction, there's the main stellar body of the galaxy. And perpendicular to it is a distribution of gas and dust. So this gas was the gas that came from the external environment of the galaxy and ended up significantly misaligned with respect to the stars. So when we see something like this in a galaxy, is a clear signature that there was an external accretion event, because you can't really generate such a big misalignment via internal processes in the galaxy. And the way these misalignments are observed is by measuring the angle or the orientation of rotation of the stars compared with the gas. And then we can measure how offset these two angles are. So for the case of this galaxy that I'm showing, the misalignment angle is 90 degrees. So it's perpendicular, but you can imagine that if you have external interactions coming from different angles, you can end up with a wide range of misalignment angles. So in case the gas and the stars end up aligned, so rotating in the same direction, the angle will be 0, so they will be aligned. But if it's misaligned, it can be all the way to 180 degrees. And that happens when the stars and the gas are in the same plane, but they rotate in opposite directions. It's called counter rotation, and when the stars and the gas rotate in opposite directions. So we can measure these misalignment angles, and then we can use them as diagnostics to infer, was there an external accretion event in the past of this galaxy? And if we see something, a large misalignment angle, usually larger than 30, 45 degrees, this means that there was an external accretion event. If it's below this, within the uncertainties, they could still be aligned. So for the rest of the talk, if I refer to misaligned galaxies or galaxies with misalignment, I'm referring to large misalignment angles above 30 to 45 degrees. So the question that we wanted to address in our work was, if we have these interactions, the gas ends up misaligned, can it fuel the AGN? So can this process contribute to fuel the black hole in the center of the galaxy? And the answer to that is yes. And for the rest of the talk, I will show you how we know that. So the evidence that it's pointing towards this being a viable mechanism. So to do this, we needed a very large sample of galaxies, and we need to have information on the motions of the stars and the gas. So we needed data cubes, so 3-dimensional data where we can measure the maps for the velocity of the gas in the stars and compare them. And we did this by using the data from the SAMI survey in Australia. So this is a large survey of local galaxies that have the data that is necessary to do this study. So we use this survey, and what we can extract from it is the maps of stellar and gas velocity. So what you see here, the map on the left is a map of stellar velocity. The map on the right is gas velocity. So we extract this for each galaxy. We extract the velocity of the stars and the gas at each location in the galaxy, and then we can build these maps. So in green, this is the angle of rotation, or the angle of rotation for the stars and the angle of rotation for the gas projected in the sky. Blue represents velocities towards us and red away from us. So you can see if we compare these two maps, which were taken for the same galaxy, and we look at how the rotation behaves, we see that the rotation between the stars and the gas is misaligned by 180 degrees. So they rotate in opposite directions. So for this specific galaxy, we measure the difference in rotation and we say the misalignment angle is 180 degrees. So we can do this for every galaxy of our sample and obtain what is the misalignment angle for the gas and the stars for all of them. And then the second step is to look at how many of them have AGN. And we do this mostly using optical line ratio diagnostics, but we also cross-correlate our sample with multi-wavelength catalogs of AGN. So we find how many of these galaxies have AGN. And our final goal then is to understand, if we look at the misalignment angle between the stars and the gas, do the galaxies that have misalignment show a higher fraction of AGN or active black holes than the others? So here I'll show you one of our results. So this figure in the x-axis shows the misalignment angle between the gas and the stars. So again, anything that it's between 0 and 45 degrees, this is aligned. So we assume that the stars and the gas are aligned within the uncertainties. But if we see large misalignment angles, so this is the group on the right, this means that there was an external accretion event. And in the y-axis, I will show the fraction of AGN in each of the samples. So we separated our sample into two groups: galaxies with aligned gas and stars, galaxies with misaligned gas and stars. And when we looked at the fraction of AGN, and we found that the fraction of AGN was much higher in galaxies with misaligned gas and stars. So this was the first time that we could show this observationally. And this means that the presence of misaligned gas is a candidate for a fueling mechanism. So there's a connection between the presence of the misalignment and a higher fraction of AGN. And we're looking for mechanisms that can drive gas to the center. So this points towards this being an AGN or a black hole fueling mechanism. And the difference between the two samples is significant. We also looked at the type of galaxies that we had. And what we saw was that the early type galaxies, so these are galaxies with a low level of star formation, so they're basically old galaxies, they dominate the trend that we observe. And this is not unexpected, because it has been known that early type galaxies show a high fraction of misaligned gas. And the reason why this is, so you can think of, if you start with a spiral galaxy that has a large amount of gas to start with, and you have an external accretion event, the amount of gas that comes in will dissipate with the gas that's already there in the galaxy, and the kinematic misalignment will be short-lived. So it'll be difficult to observe it. While if you have an early type galaxy, it has a lower amount of native gas to start with. So this external accretion event will basically replenish or even build the gas reservoir that the galaxy has to form stars and to fuel the black hole. And the misaligned structures will be long-lived in these types of galaxies. So from simulations, they're expected to be long-lived for 1-2 gigayears or more. So this is why early type galaxies are the ones where we're seeing this trend. And it seems that this fueling mechanism may be more important for early type galaxies. And we have some ideas from numerical simulations as to why this misalignment could be causing the fueling of the black hole. So if you have, from numerical simulations, it has been seen that if you have misaligned structures, so gas or stellar misaligned structures, what happens is that it will promote the inflow of gas to the nucleus of the galaxy. And this could be due to stellar torques, if there's a stellar disk, or via gas dissipation, for example. So these simulations show that there's this trend of gas inflow to the center, but now we've shown observationally that there's actually a link between presence of misalignment and the fueling of the black hole. So we're going in even to the smaller scales. And what we wanted to do next was to study a larger sample of galaxies, because it's very important for this kind of study to have enough galaxies to start with, because we're looking at effects that do not occur for all galaxies. So if we want to have something that is statistically significant, we need to start with a large sample of galaxies. And what we also had access to was the MANGA survey. So this is, again, a survey of local galaxies with using integral field spectroscopy. So this is, again, the 3D, the data cubes that we need to extract the motions of the gas and the stars and compare the misalignment. So we looked at this sample. So our previous result was for 3,000 galaxies. This one is for 10,000 galaxies. And we see the same trend. So we see, again, an increased fraction of AGN in galaxies with misalignment. And it was interesting to do this comparison because for the first sample, we did our AGN selection. So we set our criteria, while for this one, we used a different selection criteria for AGN from previous work. So it's not dependent on how we select AGN. It seems that this trend is present in general for all of the galaxies that we look at. And the next question that we wanted to ask was, what is the driving mechanism? Is it the mergers or the external interactions that are causing the black hole to activate, or is it the presence of misaligned gas? And this is tricky to do, because if we see the misalignment, it's because there was an external accretion event. But sometimes there could be an external accretion event that does not result in misalignment. So gas and stars can end up aligned, even if there was a merger or a flyby or so on. So with the MANGA sample of galaxies, what we wanted to do was to test this. So we selected a sample of galaxies in the MANGA survey that all had visual signatures of past mergers, or interactions. And this was from the Lee et al. 2021 paper, where they did a visual classification using deep images to identify any sort of tidal features in the images or companion distorted galaxies that could indicate a past interaction. So this was a sample of several hundred galaxies. And what we did was we picked a sample and then we looked at how does the AGN fraction compare if you have misaligned galaxies or not. So basically the same study that we did before, but starting from a sample of galaxies with external interactions. And we find the same trend again. And of course, this is small number statistics because we're reducing the sample of galaxies that we're working with. But this indicates that even when you look at galaxies with external interactions, the misaligned gas is having the major role because it's still making a difference, even when you start with galaxies that have signs of interactions. So our conclusion is that the driver for this increase in AGN fractions is the presence of the misaligned gas. Of course, that's connected with the external interactions, but the main ingredient driving this trend is the presence of misalignment. Okay, so to put this into context, I showed you how external gas secretion can build or replenish the galaxy gas reservoir. So these external accretion events can happen through major, minor mergers, flybys, and so on. But the result is that there's suddenly a supply of gas to the galaxy. And when these external interactions result in a misalignment, the kinematic misalignment between the stars and the gas, we see that it's connected with a higher fraction of active black holes. So our conclusion from this work is that the presence of misaligned gas is an important mechanism to fuel black holes, in particular in early type galaxies. Of course, that this is not the only AGN fueling mechanism. There are many more, but this is one of the first direct evidence that we found of an AGN fueling mechanism that works at least in these types of galaxies, mainly early type galaxies that have misaligned gas. And you can ask, what is the effect of this, how important it is? So we're looking at low redshift galaxy samples because that's where we can have the spatial resolution and the data quality to do this study, and also the numbers. But we know that at higher redshift, probably the fraction of galaxy interactions was higher. So this process is probably more important at higher redshift when there was a higher fraction of galaxy interactions. So our conclusion, or extrapolating this study, is that this AGN fueling mechanism is likely more important at higher redshift. Okay, I'll stop here. Thank you.
Any questions? Please.
Thank you for the nice talk. Did you by any chance look at the fraction of radio loud sources in the Asian population? In those with low misalignment and high misalignment?
Yes, so we did a cross correlation with radio catalogs of AGN, and we found, I believe, only 3 of them were classified as AGN and radio catalogs, so a minority of them. We haven't done a search besides the catalog, so we haven't looked at radio data for all these sources ourselves, so just the catalog search. But yes, just small numbers that we have detected.
Hi, I have a couple of questions. The first one has to do, could you tell us a bit about possible biases in identifying black holes? For example, how complete is your black hole identification? If you have absorbed black holes, you might not see that, or whatever. And the other thing, if this misalignment is important, and if you have some kind of physical explanation for it.
Okay, so the first question, sorry, I'm having some issues with the sound, so I hope I understood your question correctly. So it was the bias in the AGN detection, right? Yes, no, you're absolutely right. So it's possible that there are more AGN that we are not detecting. So my view of this is that this is probably a lower limit of the number of AGN that really exist. So what we did was we used everything that we had access at the moment. So for all of our sample, we have the line ratios in the optical that we use to build the BPT diagrams and optically classify AGN. And then we use the other catalogs. But unfortunately, not all of these galaxies have X-ray detections. So we looked at X-ray observations in XMM, and we found, I believe it was around 10 of them had X-ray data. Curiously, you mentioned obscured. Curiously, there was some evidence that most of them were actually obscured, so higher column densities, but the quality of the data, the signal to noise, wasn't really enough in most of them to obtain column densities. Our plan is when the eROSITA data, X-ray data becomes available, we're going to search for all our sample in the X-ray catalog and see if more of them will be detected. But yes, I agree. Of course, we are biased because we may be missing some more AGN. My suspicion is that if we're missing AGN, it would be in both groups, so aligned and misaligned. So I don't think it would affect the trend that we see, but yes, we may be missing AGN. The second question was about the physical explanation for the misalignment. So the explanation that we have in terms of why misalignment is driving AGN is from the numerical simulation. So they've seen that the fact that you have this dynamical structure that it's misaligned is contributing to activate, for example, stellar torques that are driving this gas from the outside all the way to the center. And we have seen in a paper from 2021, we looked at one specific galaxy where we actually saw the gas as it was moving to the center, to the black hole. So we measured the rotation angle of the gas as a function of radius. And this was a galaxy with a stellar disk. So we saw that the stellar disk, the torques from the stellar disk were aligning the gas so that the smaller radii gas was aligning first. So we could see the gas as it was aligning with the disk. And that's the mechanism that has been suggested. One of them, why the misaligned gas contributes to black hole fueling. The other is gas dissipation as well. So shocks with any kind of native gas that was in the galaxy. The gas that comes in is misaligned, so it's likely to be shocks. But this is from simulation. So we haven't found evidence of these processes from the observational data, but it's something that we want to look into as well.
Thank you.
Okay, one final question. I have one final question. You showed us that you divided your sample like either aligned or not misaligned or aligned. What happens if you try and probe? Is it possible to probe like at different alignment angles? What happens?
Yes. Yeah, so ideally we would have like a histogram with many bars with smaller ranges of angles, so we could test how it varies as a function of the angle. So we did that, but of course, smaller number statistics. But what we see is that if we do the threshold cut at 30 degrees, 40 degrees, it doesn't really affect our results. If we split our sample into 4 bins, what we see with smaller number statistics is that you still have a peak of AGN activity at counter rotation, but you see it increasing as you go up in misalignment angle. So you see basically like going up towards counter rotation. But if we have more galaxies, we will be able to do this with better statistics. And our goal is then to see if you divide it, for example, in 10-degree intervals, how does it change? But we need, of course, a minimum number of galaxies per bin. So once we combine the MANGA and the SAMI data, our hope is that we'll be able to do that in a more robust way. Yeah, but it doesn't matter where the threshold is for our results. We've tested that.
Okay, thanks. Okay, so let's thank our
Thank you.
and that's it.